Hi, I'm Barbara Brandt, Director of the National Center for Interprofessional Practice and Education, and with me today is Connie Schmitz, a consultant evaluator with the National Center. And we're here to present a second session on fundamentals of interprofessional education and collaborative practice measurement, sources of validity, measurement error, and interpreting your results. So today's session has continuing education credit that will be awarded to physicians, physician assistants, nurses, nurse practitioners, and pharmacists. And our disclosure is that we do not have any conflict of interest or financial interest in this presentation today. So I'm introducing Connie Schmitz. Many of you were on a webinar last week for the first session. Connie is an educational psychologist in curriculum development, learner assessment, program evaluation, and educational research. She has been the consultant to the National Center and has been the point for our measurement collection. So many of you visit that part of our site. Her experience is in the academy, foundations, and government agencies, and she is a scholar in health and human service evaluation with over 30 publications and 45 technical reports. So your feedback is very important to us as we help to serve you. I hosted a July 12th webinar about our programming, and so we are planning a process for more programs on measurement, assessment, and evaluation. This is the #1 request of the National Center. So your feedback from today is critical. And please complete the survey, a quick quiz, and answers will be mailed out to you. And I am going to turn this over to Connie.
Great. Thank you, Barbara. And I want to welcome all of you who were at our webinar last week and those of you who are joining us for the first time. I want to especially thank people who have filled out that pre-survey. I was able to look at the results earlier this week from last week, and it was very helpful for us. Made me understand a little bit more about who is interested in sessions like this and what it is that you need to know. As Barbara said, the National Center has been very busy with doing a lot of programming around this area, and I just want to put in plugs for 2 upcoming events. One is that our colleague Jane Miller will be doing a pre-conference workshop at the National Center's Summit in later August, and the workshop is entirely on assessment. We'll review a lot of these same measurement concepts. And then in the fall, on October 1st at the CAP 6 conference in Banff, if you're able to attend that, along with 3 other colleagues, are doing a pre-conference workshop on program evaluation. And that workshop is going to be following closely the last next upcoming practical guide that we're writing, all on program evaluation, how you use teamwork assessment to evaluate IPE and other training programs. So today's webinar is really a leap for us in terms of upping the level of what we're trying to teach in terms of some basic foundation principles and concepts undergirding assessment and evaluation in IPECP. And we've created it to help those of you who want to become better consumers of existing measurement tools, more discerning readers of the research literature, and better collaborators with measurement specialists. By the end of today, we hope you feel more comfortable with some of the language used in measurement. We hope you understand the validation process better and are able to decipher some common validity statistics. So small disclosure of my own here. I've never tried to teach these topics via a webinar before, and what we've created is really packed. We're going to cover a lot of ground in the next 90 minutes. I think to get the most out of it, you might want to make sure that you have the article and handouts that we sent you earlier within reach. It's totally okay if you didn't read them ahead of time. We didn't really expect you to do so. But they will help you track some of the presentation and then later on to process it some more. We are going to stop. So you might want to have some paper and a pen ready to write down stuff you don't know and want to ask. If you were able to join us for our first webinar, you might remember a study by Doug Archibald and colleagues on the Interprofessional Collaborative Competency Attainment Scale, or ICAS. We used it to illustrate the process of reviewing a tool's relevance, in our case, the relevance of the ICAS for evaluating a large Foundations IPE course taught here at the University of Minnesota called FIPSI. Doug and I collaborated on a replication validation study of this instrument using student data from FIPSI, which is the article that we sent you today. If you don't already know, the ICAS is a 20-item self-assessment tool. It was developed at the University of Ottawa, Canada, as part of a nationally funded initiative in IPE program evaluation. Its items were written to reflect the 6 constructs listed here. And the items represent a distillation of behaviorally worded competencies that the authors derived from a literature review. And these competencies were intentionally grouped to reflect constructs embedded in the Canadian Interprofessional Health Collaborative Competencies Framework. So, here we go. We're diving into the weeds. I'd like you to take 60 seconds now to read the abstract from this study, portions of which are excerpted on this slide. You might take note of any unfamiliar words and think about what the gist of the abstract is telling you. So we're going to wait. I'm going to wait to 1:08, give you time to read through it. Think about what it's telling you. I'm going to wait just a couple seconds more. That's how we're getting you engaged. Webinars are a constrained format. Okay. I'm guessing that at least a few of you wondered what internal factor structure, effect size, change score, and item total correlation meant. And who is this guy Cronbach? And what does alpha mean? And is accounting for 85% total variance a good thing? Most important, what you probably really want to learn from the abstract is whether or not the ICAS is a good tool, whether it provides an accurate, fair assessment of students' ability to collaborate professionally, and whether it's okay to make decisions based on results. And Barbara, if you want to move the mouse around, that's okay with me. Barbara and I are collaborating here. We're a team. I apparently can't talk and advance the slides at the same time.
You ready?
I am ready. Well, these are all questions of validity. And our goal today is not to turn you into psychometricians, but to help you understand the validity arguments presented in journal studies and the validity data we just read in that ICAS abstract. So how are we going to do this? Well, we will introduce some foundation measurement concepts and then pause for questions of clarification. So have your pencils ready, or get your typing fingers ready. Then we will explain what we mean by validity data and describe five sources of validity evidence, and then pause again for questions. Then we will briefly refer you to a cheat sheet that covers some general rules of thumb for interpreting validity statistics. And lastly, we will apply those rules of thumb to the ICAS article just presented. So good. Let's start with the definition of validity and the key concepts of variance, measurement error, and reliability. Validity is more than skin deep. Not all tools are created equal. It is true that you can separate the better tools from the not so good based on their surface characteristics. As shown in the handout and on the screen by surface characteristics, We mean an instrument's overall look, tone, or feel, its basic construction and formatting, the clarity of its instructions, wording, and response options, the integrity of its scoring system, and avoidance of bias. If we're talking about an assessment using simulation, we're also thinking about the relevance and realism of scenarios, cases, or tasks. Now, some people refer to this level of scrutiny as face validity. And while face validity is important from a political and usability standpoint, it is not the same as measurement validity, and the term is generally discouraged in the measurement literature. At its most basic level, validity concerns the trustworthiness of the results of an assessment process. And as defined by the American Education Research Association, the American Psychological Association, and the National Council of Measurement and Education, validity is an integrated judgment about the degree to which evidence collected about a tool supports the way we wish to interpret and use its scores. Well, that's a mouthful. So let's let that sentence roll around in your brains for a moment. So validity is an integrated judgment, meaning we look at different types of evidence and then come up with a holistic conclusion about the trustworthiness of the data for a particular assessment purpose. So contrary to popular understanding and the way most of us speak, including measurement people who are sometimes lazy, we don't actually validate instruments. We validate our interpretation and use of its scores. Now, this is a subtle but very important distinction. And life would be ever so much easier if we could think of validity in black and white terms and say, this tool is valid, this one is not. But unfortunately, validity is not an all or nothing seal of approval, but a matter of degree, with some validity arguments being supported and others not. The evidence of validity we collect about an instrument is also very sensitive to the context in which it is used. That means that the validity data will fluctuate at least a little from setting to setting, population to population. In validation studies, researchers first state different kinds of claims or hypotheses about what is being measured and what the scores mean. They then administer the tool to intended participants and examine the data in order to test these claims. They make tentative judgments about the degree to which the claims are supported. Most important, the research community then replicates the instrument across time and place to further build its case. An instrument with a good history is one for which consistent types of validity data have been reported by different users. And when that happens, we say an instrument is robust because the validity data have proved to be stable. To clarify what we mean by claims, let's use a fictitious example of a 15-item rating tool we'll call the IPECP Leadership Scale. Some of the claims we might make about the scale are that, first, the 15 behaviors listed are the right behaviors to look for. We claim that they truly reflect what collaborative leaders do and don't do. Second, we might claim that the behaviors are so well described that different people observing trainees in a simulation scenario will agree whether or not those behaviors occurred, and those observers will score the trainees in a similar manner. Third, we may claim that the scores in the simulation setting are so accurate and so indicative of a leader's true behavior that they will correlate with separate ratings of that person's leadership as demonstrated in practice. So to test these claims, we run the simulation, collect and analyze the data, and we also collect leadership ratings from people who work with the trainees in practice. The evidence we look for might include such things as a good literature review to back up the behaviors listed on the tool, high inter-rater agreement among the raters who observe and score the simulated performance, and high correlation between the simulation scores and the ratings of trainees in practice obtained from a 360-degree evaluation form. So hopefully that example gives you a general working idea of the validation process. Let's talk now about variance. an important concept that underlies many of the validity statistics reported in the literature. And before we launch into this, I want to clarify that just for the sake of simplicity, I'm going to use the words test and scores throughout the rest of the presentation. This doesn't mean that every instrument used in IPECP is a test. In fact, most are not. But it gets lengthy and redundant to keep saying test, survey, rating tool, or the like. And I'm also going to use the word assessment through the rest of the talk, knowing that assessment data may well be used in an evaluation or research study. Okay, the understanding of variance begins with the recognition that all data vary. Now, this isn't exactly a newsflash because you already know it to be true. Whenever you give or take a test or collect any kind of information about virtually anything, responses will vary. This fact that data vary applies across the board to what we call categorical data, such as multiple choice test questions and checkbox items, and interval data, such as simple counts and circled numbers on a rating scale, or Likert scale, I should say. When studying variance in data, we are basically working with summary statistics, such as those listed here. And these basically represent features of aggregated individual data points, such as averages or percentages, and sometimes the conversion of those summarized data points into more stable statistics, such as standardized scores. You are all probably familiar with the normal distribution or bell curve, and this is the general shape that data take when you plot the numbers collected from a random sample of at least 30 people or observations on a graph, with their frequency on the vertical axis and the actual score values on the horizontal. The mean represents the peak of that curve, the average score obtained from this group. And the variance represents how far the data points extend to the left, or the low end, or to the right, the high end of the score continuum. In technical terms, variance is defined as the average of the squared differences of each data point, that is, each score, from the mean. But the important thing to remember is the larger the variance, or its derivative, the standard deviation, the greater the spread in your data, meaning the fatter the normal curve, the lower the peak will be, and the greater diversity in scores. And a small variance means more uniformity, more similarity, greater agreement. So one of the first questions we want to ask about our data in our journey towards understanding validity is, how much of the variance represents reliable, useful information about participants versus noise? That is, data that are extraneous or unrelated to what you're trying to measure. This is otherwise known as measurement error. Measurement error does not mean a mistake, nor does it mean that some individuals answered an item incorrectly. Rather, it refers to things causing the data to vary that are unrelated to what you're trying to measure. There are two basic types of measurement error. Systematic, which means the source of variance applies to everyone involved with the assessment. And random, which means really just chance variation due to whoever is taking the assessment, the day, the time, etc. Now, systematic errors can be linked to problems with an instrument, like bad formatting or wrong, bad response options. Systematic errors can be also linked to the way the instrument is administered, involving like lack of standardized procedures, or to policies and incentives that influence how people respond. Random errors really just pertain to individual differences in people, such as their native language or prior experience, their personal motivation or fatigue level. What is important for you as users of instruments to understand is that we can't do much to control random error, but we can exercise some control over systematic error. Because there's always some amount of error present, there's no such thing as an error-free assessment process. So because there's always some amount of error present, measurement specialists define total variance as whatever the true variance might be plus some unknown amount of error. Now, what we want to know, of course, is the true variance, which is the total variance minus the error. And this is where the notion of reliability comes in. By definition, a highly reliable assessment means there is little error. So this brings us to our last foundations concept, reliability. When we talk about reliability, we talk about things like precision of measurement, internal consistency, or reproducibility of scores. And as just stated, when measurement is precise, the proportion of true variance in your data will be high, and the proportion of errors will be low. Consistency means that when you have a number of items trying to measure the same thing, like communication, the scores are very similar. In fact, they correlate with each other, and they cluster together in statistical tests looking for common factors. Reproducibility means that an assessment process will yield very similar results if the assessment is given twice to the same people under the same conditions, assuming there are no intervening events that would change their performance or responses. The common reliability statistics are calculated as a proportion on a scale of 0 to 1. We call the resulting statistic the reliability coefficient, and we qualify it as an estimate. Doing so reminds us that this is the result we got from this set of data, from this particular population, at this setting, at this time. One of the more common reliability statistics is Cronbach's alpha, named after the esteemed statistician. And the alpha represents the degree to which all of the items in a scale, survey, or test are intercorrelated. We call this internal consistency. A similar statistic is the interclass correlation, the ICC. Inter-rater reliability tells you the degree to which two or more raters' sets of scores are correlated, meaning both raters tended to score the same individuals high and the same individuals low. It does not mean that the raters scored the individuals in the exact same order, however, or gave them the same score. Inter-rater agreement does that, and it is a more stringent measure of reliability. It measures the portion of times raters assign the exact same score to the same people. The most common statistic here is Cohen's kappa, named after another famous statistician. In addition to reliability, there are other techniques for estimating error, which we don't have time to go into. These include various calculations of standard errors, such as the standard error of measurement and the estimation of confidence levels, labeled CI, and they're explained on our handout. Given that measurement is imperfect and error is always present, well, how reliable should scores be? And the answer lies with the purpose of assessment. Experts generally agree that high-stakes assessments, where results affect such things as candidate selection or certification, the instrument needs to be as reliable as possible with coefficients of 0.9 and above. I would apply a standard of close to that or that, 0.85, for any instrument used for evaluation and research as well. For more moderate stakes assessment, such as classroom grades or quality improvement benchmarking, coefficients in the 0.8 to 0.89 range are acceptable. And for low stakes, formative assessments used primarily for teaching and learning purposes, coefficients of 0.7 and above are adequate. Reliability of measurement is extremely important. It is integral to validity. Conceptually, you can't draw valid conclusions about the results of a test if the data aren't reliable. And technically, in the calculation of validity coefficients, the degree of reliability in a set of scores puts a limit on the ceiling for their validity. For that reason, the National Standards for Educational and Psychological Testing does not treat reliability as something separate from validity, but as an intrinsic part of the validity argument. For more information, see the handout distributed for this webinar. So now I'm going to pause for a couple of questions on the definition of validity, variance, measurement error, or reliability.
So this is Barbara Brandt, and Connie is stopping here. This is a lot of information. Some of you will know some of it. Some of you, this will be very new to you. So this is your opportunity to ask questions. And I want to put this in context. Again, this is the #1 area of questions to the National Center. And many people contact us and say, what measurement instrument should we use? So the reason for presenting this is exactly to help you think through why that may or may not be an appropriate question to ask us, and how can we support your work by understanding some of these basic concepts. So again, those of you who are on the webinar, what kinds of questions do you have for Connie based upon these concepts so far?
And if you don't really even know how to frame your question, if you just want me to repeat something, that's okay too. And if you still are just interested in digesting it and thinking about it, that's all right as well.
Any questions? Here's a question. If we use a validated survey and alter it for our use, do we need to get permission from the author?
Well, that's a good question, and we hear that as well a lot. The answer is yes. And if you go to the Nexus website and to the assessment and evaluation page, you'll see a list of frequently asked questions, and it gives you some, I think, hopefully helpful information on why it's important to contact the author and how to do it. But more germane to this conversation, if you're understanding that validity evidence is going to vary depending on how it's used, I think that makes you hopefully realize how important it is that if you're going to change that instrument, if you're going to alter it or anything, that's going to affect the validity data that you collect. And that will make it even more important for you to do some local reliability testing before you use the instrument. Most of the instruments on the National Center's Measurement Instrument Collection page are open source. Some have proprietary, some are copyrighted, and we just paraphrase what is on the website. We really encourage you to contact the authors, even if it's an open source instrument, and definitely you're going to have to get their permission to change it.
And some of the authors or creators of these instruments like to know when and if they're being used for their own research and to advance their understanding.
Yeah.
So Connie, the slide that just to me was the most impactful was validity is not inherent to the tool.
Yes.
And we don't validate instruments, but our interpretation and use of scores. Validity is a matter of degree, and validity data are sensitive to context, and validity data fluctuate.
Yeah.
I mean, that is why we can't say this is the absolute best tool.
Well, keep thinking, and you can keep typing your questions. Or one more.
What do you recommend for using a tool or scale that has been validated and is included in some site-developed question? For example, administer separately, use a validated scale first.
I'm not quite sure if this listener is asking us to name a particular tool or I'm not sure. Can you help me understand this question?
Yeah, I'm not sure I understand. So you might actually give us a little more information. And the issue is, what do you recommend for using a tool or scale? And I think that's generic, that has been validated and is included with some site-developed question. So maybe like a local question.
Yeah, it might yes. If that's the case, it is appropriate, and I've often done it myself, is I use an instrument that has been used in the literature as is, but then I add a couple of questions at the end of my own. You just have to make sure you score those separate questions separately if you want to rely on the validity data that's been collected about the original tool. Well, I think we should maybe move on, and again, just keep typing in questions as they pop up, and we'll stop in another 30 minutes. So what constitutes validity evidence? First of all, as we will soon see, it can be either qualitative or quantitative in nature. Second, when it is quantitative, we say data, which means statistics, such as the one we've just presented. And these statistics, like reliability, are estimates that are based on a particular administration of the tool with a particular population at a particular place and time. Because there are so many different statistical techniques that can be used, resulting in so many different kinds of validity statistics, we're going to limit our conversation to just 4. Correlation coefficients, factor loadings, percent of variance accounted for, and effect sizes, as represented by Cohen's d. The concept of correlation underlies many of the statistics used in validity research. Basically, it means that 2 or more variables co-vary. That is, scores are related to each other. This slide shows a fictitious table with individual subject scores on the self-report measure of stress, followed by their scores on the measure of the symptoms believed to be related to stress. The graph shows how each person's scores for stress and symptoms are plotted. And as can be seen in both the table and the graph, scores that are high on the stress measure tend to be high on the symptoms measure, and vice versa. Scores that are low on stress tend to be low on symptoms. But it is by no means a perfect relationship. If it were, every data point would be resting on that black line representing the angle or degree of correlation on the graph. Still, we can see that these 2 variables are at least somewhat related. The question is, just how related are they? We calculate the degree of correlation on a scale from 0 to +1 or 0 to -1. And negative correlation means there's a consistent relationship where high scores for one variable co-vary with low scores on another. Either way, the result is a correlation coefficient, which can be reported to the second or third decimal. In the example from the previous slide, we saw a correlation of 0.506. Well, what does that mean? How big a correlation is that? It can depend on the variables you're studying in the context of your analysis, but one way to get an estimate of the magnitude of the correlation is to mathematically square it, as represented by the R2 number here. So if you multiply 0.506 times 0.506, you get 0.25, and that means that 25% of the total variance in this data set can be explained by the relationship between our 2 variables, stress and symptoms. In the measurement world, we actually consider 25% a credible amount. Let's talk now about factor analysis, which is an approach to understanding the internal structure and content of the test. It uses correlations to determine the extent to which item responses correlate or group together around similar constructs, such as leadership or teamwork. Often the goal of factor analysis is to identify latent factors or encompassing dimensions that explain why certain items are intercorrelated. Factor analysis can be used to explore the data empirically to see what natural groupings of items emerge, and when used in this manner, researchers look for a common theme that unifies those items, and they find a label that describes the nature of the item grouping. Factor analysis can also be done to confirm constructs that are proposed ahead of time by a theoretical model or by the content categories that organize items in the tool. In tool development, often a combination of exploratory and confirmatory approaches is used. Either way, this process helps us understand an instrument's content and whether it is measuring what we think it is measuring. Now, factor loading is a statistic that represents the degree to which an item's mean score is correlated with a common factor. We generally look for loadings of at least 0.40 to conclude that an item should be grouped with that construct. If we find a weak correlation that is under 0.40, we may discard that item or rewrite it. In the example here, for a set of items written to represent situational leadership, we would question the utility of items 7 and 8 because they're below 0.40. They may be useful for measuring something else like, I don't know, characteristics of valued team members, but they don't really appear related to leadership, even when you read them. We spoke earlier about wanting to know how much variance in a set of data is meaningful information versus noise. We're now going to ask a second and closely related question, which is how much variance can be attributed to or explained by proposed factors in a conceptual model. Let's say we have a patient satisfaction survey, and we are curious about patients' perceptions of interprofessional collaboration. That's the big bubble on the right there. We may believe, for example, that patient satisfaction will be principally influenced by the factors of leadership and team communication. But we also wonder if satisfaction will be influenced by other things, like the quality of care conferences or efficient care coordination. Statistical techniques, such as factor analysis, attempt to parcel out the proportion of variance related to each factor to see if this conceptual model fits the data. Well, why is it important to explain a variance, the amount of variance? Being able to explain a high proportion of variance in the data is integral to validity. As again we've said before, any unexplained variance represents error, noise. In reporting results of factor analyses, authors may also use something called the eigenvalue statistic to convey the amount of explained variance for a particular factor. And the eigenvalue statistic, to interpret it, needs to be at least 1.0 in order for that factor to be considered an important factor. Some authors simply report the proportion as a percentage, as in 25% of the variance is explained. Test A on the left shows a test where perhaps 75% of the total variance in the data can be explained by a combination of factors, and 25% looks like something else. We don't know what. Accounting for 75% of total variance is a positive finding. In contrast, we would view the findings from Test B as troubling. If we like the instrument and know it has a good track record with other people, we might retrace our steps to see whether any problems with data collection, data entry, or analysis occurred that might explain why we got that result. And if we can find no anomalies, we would have to conclude the instrument is not measuring what it was designed to measure, at least for our population and setting. I'm sure your heads are hurting, so good news, this is the last validity statistic that we're going to talk about, and it's the effect size. Effect sizes can be calculated in different ways, but all have the goal of quantifying the magnitude of change or the size of differences between sets of scores. For example, pre-post test scores, or differences between treatment and comparison groups. The calculation of raw effect size is simple. Everybody can do this. It's based on mean scores. And using the example, the raw difference between pre-post test scores is simply the mean post-test of 20 minus the mean pre-test score of 15 for an effect size of 5. 20 minus 15 is 5. This is useful information, but it has a major limitation. Once we try to compare effect sizes between items and tests that use different scales, we run into trouble. An effect size of 5 on a scale of 20 is quite large, 25% of the entire scale. But an effect size of 5 on a scale of 50 or 100 becomes only 10% or 5% of the scale, which is not so much. To interpret effect sizes across items, subscales, or tests that use different scales of measurement, we need to translate the raw difference into the same unit of measure. This is called standardization. And we accomplish this by dividing the raw difference by the standard deviation of the populations being tested. In the case shown, the standard deviation of the data being analyzed is 4.5. So the raw difference between pre- and post-test scores was 5. 5 divided by 4.5 equals 1.05. represents a very large effect. Rules of thumb for interpreting how excited to get about standardized effect sizes are listed below and in the handout. Okay, now that we've talked about correlation coefficients, factor loadings, proportions that explain variance, and effect sizes, we are ready now to move on to the meat of validity evidence. We'll talk about the 5 sources of validity evidence we look for when developing, adapting, or using an instrument. The 5 sources are content, response process, internal structure, relationship between scores and other variables, and the consequences of testing. I'm going to go through each source one at a time. I will first explain the claim that is being proposed, and then list some common types of evidence used to support the claim. For examples of validity claims and evidence in the IPECP world, take a look at the handout. Claim 1, content. Establishing the validity of an instrument's content is important. Well, why is it so hard? Why is this a problem? Well, logistically speaking, a single instrument can't possibly measure everything there could be to measure about some facet of IPCP. So, test developers therefore have to select and edit what goes into a tool. And in classic test theory, we acknowledge that the items, tasks, or cases we write to represent the domain of interest really are just a sample of all the many possible items, tasks, or cases that could have been created to represent that domain. The content validity claim, therefore, is that whatever was included in the tool is a good sample. It's the right sample. Maybe it's even a better sample than someone else's tool measuring similar stuff. And the threats to content validity, as shown in the bubbles on the right, are that the instrument content either underrepresented what you're trying to measure or includes too much relevant stuff. Feels like we've heard this before, right? There are many ways to go about establishing content validity, the most common of which are listed here. Literature reviews can detail the connection between tool content and theoretical constructs and/or prior support for items from previous research. When constructing items to represent various domains of knowledge, skills, behaviors, etc., developers usually build what we call blueprints to ensure proper coverage of each of those domains. Items may also be reviewed by subject matter experts or by leadership consensus panels. I often think of all of this evidence as building an instrument's provenance with the basic goal of justifying its content. Claim 2, response process. As the name suggests, this source concerns how people respond to an assessment. And the problem here is that tests are not real life. They are artificial events, constructed to elicit responses from people which we hope represent what they really know or believe, perceive, can do, or cannot do. Even if the content of the assessment is grade A perfect from a rational point of view, we need to be concerned about whether the participants understand what is being asked and can respond appropriately. The response process claim, therefore, is that the assessment provides people with a fair opportunity to respond authentically, honestly, to the best of their knowledge or ability. It is not about them getting the right answer. Now, the same process also includes raters and their ability to respond authentically, accurately, to the best of their knowledge or ability. Evidence of response process validity is often obtained during pilot tests, when we sit down with potential raters or respondents and ask them to read the instrument aloud and talk about what they think the instructions and questions mean. Known in some circles as cognitive interviewing, this process can yield very rich data on how people mentally process assessment items and tasks. The process can uncover confusing instructions, wording, and discrepancies between how people would respond to the test as opposed to how they would respond in real life. Another strategy is to have an external observer watch people during the administration of an assessment. This may reveal non-standard procedures, unintentional cueing or bias on the part of instructors, unequal opportunities to respond across settings or scenarios, or just plain confusion. By observing participants, we may also gauge the quality of their engagement. All of these things can affect the validity of the data. Remember, validity of the data, not the instrument. After the assessment is over, analysts typically check the data for blanks and other anomalies in score sheets, such as question marks added by participants next to an item, suggesting they didn't know how to respond. Maybe you've done that sometimes when you couldn't find a way to answer a survey the way you wanted to answer. Lastly, looking at the inter-rater reliability and agreement coefficients, along with rater debriefing sessions, may help uncover problems with rater scoring. We move now to the third validity source, internal structure, where the bulk of traditional psychometric efforts are spent. The underlying problem here is that it is really hard to write good items in tests or cases. It is hard to write the right number of items, that is, a sufficient number, but not so many that the test becomes too long, tedious, or expensive. It is especially hard to write items to represent distinct but closely related constructs. And even when we think we've got good items from a content validity and response process perspective, the items may just not function as we expect. And we find this out when we investigate the items using data from sample populations or our own setting. Many different types of claims may be advanced to test an instrument's internal structure. The most pertinent ones are that measurement error is low and reliability is high, that items meant to measure the same construct are related, and that factors are stable and explain a high proportion of overall variance. Again, there are many different statistical techniques that are used to investigate the internal structure of an instrument. And by now, hopefully, some of the ones listed on this slide will be sounding familiar to you. We've already talked about Cronbach's alpha, which can be computed for clusters of items that make up a scale, or to factors, or to the entire instrument. Ditto for the interclass correlation. The item total correlation tells you how each item's mean score correlates with the mean of the total test score, and whether removing any items would increase or decrease the internal consistency reliability of the total test. Generalizability is a more sophisticated type of reliability analysis that parcels out the sources of variance to different facets, with facets meaning such things as people, professions, institutional sites, rater groups, etc., as well as test content. We've already talked about exploratory and confirmatory factor analysis. And there are other procedures that similarly look at the fit of the obtained data with an expected model of how the data will behave. All of these things are done to understand what the instrument is actually measuring and how accurately it does so. Claim 4, relationship with other variables. What we've been talking about up until now concerns the content of the test, its ability to elicit authentic responses from participants or raters, and the relationships between items within the instrument. What makes scores meaningful, however, is knowing how they relate to variables outside of the test. Otherwise, it's really hard to interpret the value of a test result. A score of X is simply a score of X. Nice to know, but so what? What does one do with it? So scores gain meaning if we know how they relate to other things. As in, if they have these symptoms, they may have stress. Or if she scores well on a leadership test and simulation, she'll be a good leader in practice. So depending on the circumstances, different types of claims can be investigated, and I will focus on just 4 of them. A claim of convergence, sometimes called concurrence, means we expect scores from one instrument to correlate with scores from similar related items, either from the same or other surveys or tests. In contrast, a claim of divergence means we don't expect scores from an instrument to correlate with random factors or characteristics unrelated to what we're trying to measure. Some people call this discriminant validity, but I prefer to use the word discriminant when I expect results to discriminate or differentiate between groups who would be expected to respond very differently to an instrument. A claim of prediction means that knowing the results of an instrument allows us to predict how the participants will perform in the future, or that the findings prove a relationship between what the instrument is measuring and a desired criterion or outcome. We now arrive at our fifth and last source of validity evidence, the consequences of testing. The problem here is that it is hard to do assessment well, and even good assessment can lead to unintended consequences. The claim to investigate is whether the benefits of assessment, such as the results help you with planning, they improve student learning, they give you better predictions, lead to fairer decisions and policies, whether all of that outweigh the costs. And costs include money, time, people. They also include potential misuse of scores, political fallout from the results, and a failure of the test to hold up over time. It can be difficult, and it can take time to gather evidence of consequential validity. Usually a test has to be in use for a while. But one of the easier methods is to get feedback from all of the participants in the assessment regarding its value. This means students, practitioners, staff, raters, faculty, supervisors, etc. It is also relatively easy to tally actual resource costs, such as the time required to administer and respond to a survey, the time required for a simulation with debriefing, and the cost of raters. More difficult is looking for potential misuses of an assessment or the resulting scores. Misuse includes such things as like participants gaming a simulation, students sharing copies of assessment checklists, instructors teaching to the test. When test results lead to clear-cut decisions, like requiring teams to attend mandatory training, it is possible to analyze the decision accuracy of the cut score used to determine when an individual or team should be required to take the training. This requires a research study of itself, in which people who score low at baseline are randomized to either training or no training groups, and tested later on a criterion performance measure. If the individuals who receive no training still perform well on the criterion measure, the cut score needs to be raised, leading to fewer people sent to training, or the test abandoned. Last but not least, if a test has been used for predicting desired outcomes, such as lower visits to the ER, higher patient satisfaction, and the like, it clearly has utilitarian and social value. And now we're going to pause again for any questions that you might have. They're about the nature of the validity evidence and the validity statistics that we talked about, or the 5 sources of validity evidence.
And I would also say, if any of you have examples from your experiences that this content sort of raised some of the issues that you grappled with, we would love to hear from that. So we do have a question. One says, is there any tool for measuring provider biases towards patients and how interprofessional approach would eliminate it?
Well, I suggest that you go to the literature. I am not aware that we have any tool like that in the measurement instrument collection. And I'm not sure I would know how to answer whether using an interprofessional approach would eliminate some of the biases towards patients. I think more important to me is knowing that you understand there are steps you can take to find out whether any tools that you might find in the literature are going to work for you or not. And that would be, again, looking at the relevance of the tool for your situation, and then walking through some of these questions about the validity data that may be reported for that tool.
So we have another question, but it's very specific to the network and the National Center Data Repository. So I suggest that we actually not talk about that in this particular webinar because it's not relevant, but we'd be glad when we're going to be discussing it at the summit, and would be very happy to talk to you separately on these questions. Another question has come in, is what are common validity issues that are found with using tools used to measure perceptions of interprofessional practice as well as behaviors in practice?
That's a really good question. I'm trying to think in my head whether validity issues are specific to the content of an instrument. I think what I'm thinking about is, for example, a lot of the instruments that measure perceptions of interprofessional practice and behaviors are self-report, and they're subjective instruments. I think, again, just trying to understand the internal structure of the tool to see how it's really defining interprofessional practice and what are the behaviors being used, whether there's some support for the content validity of the behaviors that are being listed there, the perceptions. I'm not sure I'm really getting at what you might be asking. If you want to say some more, that might help me.
So the issue is the difference between perceptions and behaviors in practice.
Oh, if that's what it is.
That's my interpretation.
Okay, yes. I think this probably leads to it's possible to never rely on a single instrument if you're trying to understand phenomena that are happening, and person's subjective perceptions of relationships are really important. But if you're trying to get more at concrete behaviors, whether they're doing things or not doing things in practice, then it's much better to also have some objective source of data for that. And that goes back a little bit to some of what we talked about in the first webinar about the source of the data, whether it's self-report, subjective versus objective. So having observers, sitting and watch a group of people around an interprofessional case conference or a patient encounter and sort of report on various facets of how people are collaborating, I think that would be very useful to have that as a companion to the self-report.
So this is a great question, is how does the ICAS tool evaluate a course? Please give an example.
Well, the best example is the article that we sent out ahead of time for this webinar. We used the ICAS to evaluate our large foundations IPE course called IPECP. And that's what I referred to at the beginning of the webinar, and we'll see how we use validity data to sort of confirm our decision to use the ICAS for this course.
And let me just say that we are actually looking at using the ICAS more broadly in the National Center. And because we have substantial experience with it, it is a self-report of behaviors. And so we use it, as Connie said, in our very first course that is taken by over 1,000 students, but then we actually use it at various times during a student going through their curriculum. So we had a group of students come in and talking about what we should be using in the National Center, what were experiences. And what was really impressive about talking to the students who've used this and had it implemented multiple times is they actually talked about the items, helping them understand what expectations of interprofessional behaviors are for them. So they were becoming familiar with the tool. The faculty had talked about the tool, but this is a really great example how assessment can actually inform development and inform instructors and courses. So it's not an evaluation of a course, but as Connie has said, it's one way of getting a measurement when you use this particular tool, but also other tools.
That's a really great example, and I didn't know that, Barbara.
I know, I'm sorry, I didn't tell you. Connie was our evaluator, is our evaluator, so.
So that's a really good example of, sometimes people say, well, I want a tool that's good for assessment, or I want a tool that's good for evaluation. A measurement tool can be used to assess learners and can be used to help them develop the skills that are being measured, just as Barbara said. That same instrument can be used to evaluate a course. That same instrument can be used to do some research. One caveat to what Barbara has said is once you start using an instrument multiple times for the same student as they go through a curriculum, it loses its value as an evaluation tool. And that is because they are learning to the test.
Yeah, that's true.
Just as teachers can teach the test. So again, sometimes you have to think through when you're using the same instrument for multiple purposes, but in general, I'm all for learning, and if it's being used that way, I think it's great.
But I think that speaks to the context question also.
Yeah, and maybe I'm still thinking about a previous question about what are the sort of known validity issues with self-report. Anytime you use self-report for novice learners, you have that problem of asking them to report on either what they believe, they know, or they think, or they can do, when they don't even really know what you're talking about. So the pre-post issue has come up a lot for those of us who teach foundation learners. And for that reason, we used in the ICAS replication study, as did Doug Archibald in the original study on the ICAS, the technique known as retrospective pre-post. And that means you don't ask students actually at the beginning of the course to fill out the survey. You ask them only after the course to think back about what they knew, what they thought or they could do at the beginning, and compare it to what they know or think now. And actually, when you fill out your post survey, we're going to do that same thing to you. So you'll get to experience it. So I think we're ready to move on now. So you're wondering, okay, Connie's telling me I got to go look at validity evidence before I use an instrument. Where can I find that evidence? Well, if you're using a commercial test, the developers publish manuals that come when you purchase it. And with open access tools, some authors will prepare user guidelines, which may include norms or validity data. Additionally, there are reference manuals published by measurement societies. You can go look up a particular test. You can, of course, find validity data about instruments in the National Center's measurement collection. Each tool has a descriptive profile that includes citations as well as a summary of validity data from the primary article. But the best source of information comes from journal articles. And having spent a fair amount of time looking for validity evidence in journal articles, we have prepared a handout for you with some tips. And hopefully you will find this helpful. So where are we in the agenda? We are coming close to the end of our presentation. We have one segment left. We will talk now briefly about the problem of deciding when validity claims have been satisfied and refer you to a handout with some rules of thumb. We will then apply these rules of thumb to the ICAS instrument and study findings we presented at the beginning of this webinar. Now that we've talked about the nature of validity data and the challenge of providing evidence to satisfy 5 possible types of validity claims, you may be thinking, well, is it really possible? Does it ever happen? Since validity is a matter of degree and not an all or nothing approval rating, at what point do you say, we have enough validity evidence to satisfy this claim? We have enough evidence of validity to make decisions based on these scores. And this brings us back to the definition of validity, which calls for an integrated judgment based on the quality of validity data and the intended use of a tool for particular assessment purpose and context. And our overall rule is, the higher the investment in a test, the greater the consequences of its results on individuals and programs. Then the broader number of claims need to be argued, and the higher the standard for acceptance. Rarely do we make a determination about validity based on a single number or result. As said before, we look for a pattern of positive signs throughout the study and the replication of those signs across users. That said, we need to have some guidance on interpreting individual validity statistics. And I have prepared some of the more common rules for the top 10 statistics you need to know on a handout, some of which we've already discussed. And if we have time at the end of this segment, I'm happy to go over that handout or any of the other handouts that were distributed. So let's try now putting all of this together by returning to the ICAS example we began with. In our replication study, we tested 3 validity claims: content, internal structure, and relationship to other variables. We also asked 3 students to look at the test and comment on it, and they had no problems with understanding. But I wouldn't say we looked at response process in any depth. We also did not consider consequential validity in any depth. As discussed in our first webinar, before administering the ICAS, we reviewed the original validation study by Doug Archibald, its description of tool development, and its findings. We compared the 20 items with 60 course objectives and the core IPECP competencies identified by the Interprofessional Education Core Consortium. And we found generally good alignment with a few exceptions, namely the FIPSI course did not teach patient-centered care per se, and the class sessions did not involve any actual patient interaction. Teamwork was modeled based on fictitious case studies. Thus, it would be hard for students who had not been in a clinical setting before to assess themselves on their ability to deliver patient-centered care. After administering the survey at the end of the course, we analyzed students' self-reported pre- and post-scores on the 20 items. We calculated standardized effect sizes for each item based on their mean scores and the standard deviation of the combined pre- and post-data sets. And what we found was a largely encouraging pattern of moderate to strong effects for the areas in the course we spent the most time on, and smaller effects for the item measuring patient and family-centered care. And on this slide, we see the actual data from one of the tables in the article, showing the organization of the tool's 20 items by the 6 proposed constructs there on the left, and the item itself in the middle column, and the effect size under the column headed Cohen D, and its classification as either a small, moderate, or large effect, according to the rules of thumb presented earlier. So if you look through them and you see the colors, the items that I've highlighted, you'll see that we were strong in areas. Well, first of all, course instructors were happy to see so many moderate to large effects. But we were happy that the pattern of effects aligned with FIPSI content, as this provided additional evidence of content validity. For internal structure, we focused on factor analysis, since that was the key technique used in the original study. And the original study found 3 main factors accounting for 73% of total variance, not the 6 constructs proposed in their model. In the replication study, we were unable to replicate either the 6 or the 3-factor model of the original study. Instead, we found a single underlying factor accounting for 85% of total variance, which is very high. Additionally, the internal consistency reliability of this single factor was really high, 0.96. When we calculated the item total correlations, we learned that the deletion of any item in the survey would actually lower its reliability. So we argued that all 20 items of the ICAS should be kept, but only the total score should be reported. Lastly, we considered what external variables might help us better understand the meaning of ICAS scores. To do this, we created one new question for the survey. We asked students how much their overall ability to collaborate interprofessionally had changed over the course of FIPSI. We asked them whether their ability was much better now, somewhat better now, about the same, somewhat worse now, or much worse now. This type of item is sometimes called a transition item or a global item. Then we correlated each of the 20 original ICAS items with this global score. More specifically, we correlated the mean effect sizes for each of the 20 items and the mean global item score. And for 18 of 20 items, the correlations were above 0.440, a threshold we discussed earlier, and that was a positive finding. To summarize, we felt the content validity of the ICAS was high for our IPE course. Its items were sensitive to our course content. In terms of internal structure, although the factor analysis results did not support the model as originally proposed, we felt having a single underlying factor with high internal consistency reliability and a high proportion of explained variance was very good. Now, if you're a researcher, the lack of differentiation between presumably independent constructs such as communication, collaboration, team functioning, etc., would be problematic. They would want to redo the instrument. We argued that since we tend to teach these things holistically, and by nature they are similar or overlapping to begin with, it made sense that the responses to many of the ICAS items were intercorrelated. And since our goal was not to prove a theoretical model, but to evaluate a course, proof of separate constructs was less important to us than the combined proportion of explained variance, which was high. And lastly, as external variables go, our use of that separate global item measuring overall change was, well, okay, relatively weak. A much stronger external variable would have been a rating supplied by an external observer. The reality is this required greater resources and time than we had at our disposal. We also felt that for a foundations course, observing preclinical students in a practice setting was probably premature. The strong pattern of correlation between most of the items and the students' overall sense of how much they had improved gave us confidence that the survey was measuring what we wanted to measure, namely, improved interprofessional collaborative competency. For all of these reasons, we adopted the ICAS as one of several measures of course evaluation. We felt it was a good survey. It provided as accurate and as fair an assessment of interprofessional collaborative behavior as self-report can be for preclinical students. And we believed its results would help us evaluate the course and even identify some areas for improvement. We've come to the end, and we hope you've gained an appreciation that validity is more than skin deep. Surface characteristics of tool construction matter, but proof lies in the validity data. We hope you've also gained an appreciation for the difficulty of determining validity and are more skeptical of statements qualifying tools as reliable and valid. It is important to look for tools with stable evidence of validity data across settings. Perhaps even more important, you should try to collect some response process validity data from your own setting prior to adopting a tool. This is extremely important if you're altering the tool as well. You should try to limit systematic errors creeping into your data by standardizing administrative procedures and monitoring implementation quality. You should build in time to calculate local reliability data. Last but not least, we encourage you to seek out measurement professionals in your home institutions or communities. We are educable, you know, we measurement people. But if you can teach us at least one person about your world and how IPECP happens in it, he or she may become an invaluable partner.
This is Barbara Brandt. Before we go to the closing slide, what I want to say is that this is your opportunity to speak with a measurement professional who has substantial experience working in clinical environments. She worked for a number of years for our Department of Surgery and did quite a bit of measurement work, not just with the University of Minnesota Surgery Department, but Mayo Clinic. You were a consultant for 12 years to major foundations. Kellogg, you did work with the RWJ, Hartford Foundation. And so when Connie tells you to become a friend with a measurement professional, she had to learn about the field of IPE.
Definitely.
So it is not, there's not a whole bunch of IPE experts sitting around waiting to work on measurement. So it really does take a relationship to develop. She read a lot of the articles. She became introduced to the Journal of Interprofessional Care. We threw her into the fire of looking at the University of Minnesota's curriculum. And so the ICAS work really did come out of our first year course that over 1,000 students take. So she became, I would say, an expert in IPE, and we've lifted her up into the National Center work. So all of the great stuff you see on our website is as a result of Connie, and I think she's one of the experts worldwide in this particular field. But I do want to say that it does take that working relationship in context with a measurement professional to really learn our field, and we need to be developing more and more Connies. The last thing I'm going to say is actually what she was going to say, to underscore that both of these webinars are freely available. We hope you go back and use them and listen to them. And also we have the primer, which Connie and her colleague Michael Cullen produced. It's freely available. And then we do have, for a small fee, the practical guides. And again, this is to help you develop your, not expertise per se, but a working knowledge of the content and concept so that you can work with a professional on your IPE endeavors. So Connie, you might have had some other things.
Well, I've got a couple of thoughts now. First of all, Barbara is so right. She really spent a lot of time working with me, as with other people from universities, academic health center, so I could understand what the IPE world was about. I didn't really get a sense of that when I was in surgery.
Yeah.
There are measurement people. You can find them in various places. My title, I'm an education psychologist, but a lot of my skills are also shared by clinical psychologists, by organizational psychologists, certainly by epidemiologists, biostatisticians. And if you are anywhere close to a university or have access online to developing a relationship, you can find them in schools of education, schools of public health, schools of medicine and nursing too. As I said, we are educable. It may take some time before people like me get to understand your world. But, I found it a really wonderful world, fascinating and extremely compelling. There was something else I was going to say. I do want to also give acknowledgement to some of my colleagues on the next slide.
Yes. And people are starting to send us questions in. Keep
Okay.
going, and we'll take the next slide, and then I'll read a couple of questions. Yeah.
So these are sort of my go-to circle of people that I've worked with over the years. I just want to acknowledge them. Michael wrote the primer with me, and David Rudasovich did a lot of the actual analysis for the ICAS. Jane Miller, wonderful colleague, and I've worked with for many years in simulation and Unity Park. Okay.
So we have someone who is giving us her name. Her middle name is Schmitz. That's interesting.
Wow.
A cousin.
All right.
And it's from the university in Brazil, and she's doing her doctorate on interprofessionalism. And we're getting a lot of these kinds of people contacting us and looking for training and education courses. We can actually walk you through some of our website and talk about what's available out there. But we'll be in contact with you. Thank you. Any other questions? And most of you hung in there with us, so we're really
That's
pleased.
awesome.
And again, the reason we're doing this is to make this freely available. You know, we want to grow the field and think it's really, really important that those of us who work in the field develop a working knowledge of the principles and do seek out professionals to help support and advance the work.
Yeah.
Any questions? This is your opportunity to ask a question from a professional.
I'm also willing to share with you my email address. If you have your pencil, it is schmi002@unn.edu. And if you lose that and you just contact anyone at the center, they can forward a question.
And how you can, there's on our website, on nexusipe.org, you can also send a question to us for Connie. So another minute or two to see if there's any questions, and if not, we'll close down the webinar. But again, this will be freely available for you. We're very excited about supporting this aspect of your work. Any questions? Connie, do you have any parting shots? If we
Well, again, I feel your pain in that you may just want us to give you the fish, in other words, tell you what instrument to use rather than try to teach you to fish. But I think it's really important that the field of interprofessional collaborative practice is going to advance. It needs to prove its case. It needs to prove that it has some impact on the AAA, patient satisfaction, improved population health, and reduce costs of healthcare. It's extremely important to do that. We can't do that if we don't really understand how to use measurement tools well and how to select them wisely and how to work with measurement people to design rigorous studies. I am excited about the program evaluation workshop that I'm doing with Lauren Collins from Thomas Jefferson University and Barrett McCallick from the University of Delaware and Doug Archibald from the University of Ottawa. We're doing that in the CAB conference, and I encourage you to look at the program evaluation practical guide that should come out, I think, late fall.
Mm-hmm. And then Jane Miller will be doing a pre-session on August the 20th, and that's been filling up at our summit here in Minneapolis.
So please fill out the post survey and take a stab at the quiz. It really would help us to know, how the best we can support you and further our mission. So thanks very much.
Thank you.